Did you hear that? No, you didn't hear it, but okay. So now we're recording. Let me move myself up there. All right. One thing interesting about the calendar, I like to always talk about, I like calendars. So one thing about February is that Fridays are multiples of seven. Every month, a certain day of the week is a multiple of seven. So this time it's Friday. The other thing that's cool about this is that notice that the first 28 days of March are the same days of the week as the first 28 days of March. You see that? And then, of course, March has 29, 30, 31. Now, occasionally, every 4 years, March has a 29. So, but it still would work. The first 29 days then would be the same. And the 28th of February is my brother's birthday, my brother Joe. So I got to wish him a happy birthday. He lives in Philadelphia. Anyway, and the other thing I want to point out, so you can look forward to it, because part of the benefit of the midterm break is looking forward to it. Yahoo! Diana likes when I say Yahoo. So the spring break's coming, and remember, you get Friday off. That's a travel day if you're traveling anywhere, and then you get the whole next week off, and then we start again on March 17th, which happens to be St. Patrick's Day. Okay, any questions? All right, I'll grade the quizzes and the homework, and then I'll be able to see if you have any difficulties. And by the way, when I grade the quiz, I give partial credit. Like there was a quiz the other day where everything was done correctly, but the homework, everything was done correctly, but the calculation didn't come out right. So they got most of the credit for that because they had everything done rightly. They just made a math error. Okay? All right. Now, usually this always happens. They get stuck. So did everyone turn in their homework? Now, the active chem homework for chapter 13 is going to be due next Friday. Okay? So do that. You have calculation. There are some calculations in there. So if you have questions, again, I always recommend that you do your let me move this over here so I can see you, Ife, better that way. And I like to see the students. So always do your active chem homework problems in your notebook. Put the chapter 13 and the question number. And so then, when you're studying for an exam, you can look over the problem again. And secondly, if you have a question, take a picture of it and send it to me. Some students have done that this year, and then I can help you. Okay? And if you need further assistance on that question 10, let me know. Yeah, but do the calculation again and see if you get the right answer. All right? Good. Now, turns out, pardon me, two of you did not go on the trip. So I thought there was only going to be 4 students here today, but I'm glad you're here, by the way, Ife and Zoe. But if you go on a trip like that and you're going to miss class, please, you should inform your professors ahead of time. All right? And there was also an email, but you should always inform your professor ahead of time that you're going. That's a professional courtesy. And just like if you're going to miss class and you know it, you should let the professor know. Or if you're sick, you should let the professor know, ideally before class, but if not, after class. Okay, I'm going to have to do this. Okay, I'm going to take a message there. I hope the appointment didn't get canceled, but all right. And I'm going to continue mentoring. So Zoe can't do it. So Gabi, do you have 5 minutes after class so we can have a little mentoring session? Okay, and let's go with Diana. Diana, you got 5 minutes? Good. All right. And we are recording. Okay, so let's see. Go away. Get this thing out of here. Okay, good. That's it. All right, now we're going to do something very, very, very exciting today. Mr. LeChatlier, a Frenchman, discovered this principle by observing many chemical reactions. He was able to predict which way a reaction would shift after a disturbance to the reaction in order to reestablish equilibrium. So if there's a stress to the system, to the chemical reaction, remember the system is what's under study, and now the system is going to be the chemical reaction. Remember, everything else are the surroundings. Remember that, the systems and the surroundings from the first semester? Remember that? System plus surroundings equals what? Begins with a U. System plus surroundings equals the universe. Okay? But the system is the subject of study. In this case, it's chemical reaction. Now, if you stress a system, it's going to react to relieve the stress. It's either going to shift toward the products or toward the reactants. I apologize for my typo, by the way, on the quiz. My bad. Okay, so this discovery was called LeChatlier's Principle. And in other words, he discovered the way nature behaves when a stress is added to a system. What are some stresses now that we can do to a system, which is our chemical reaction? We can add or remove products. And when we do that, equilibrium will reestablish itself, but it has to shift left or right toward the products or reactants. If you increase or decrease the pressure, and if you have all gases, it's going to mess up the equilibrium, and then it will reestablish itself by shifting one way or another, left or right. And by the way, increasing volume, as we're going to see, is another way to change pressure. If you increase volume, pressure is going to go up. If you increase volume, if you increase volume, pressure is going to go down because there's less collisions. They're far away, particles are far away. And if you increase pressure, if you increase the volume, wait a second. If you decrease the volume, the pressure will go up because there's many more collisions. Pressure is due to collisions of the particles against the sides of the container. And we'll be going over that several times. If you increase or decrease temperature, that's the same thing as adding or removing heat. And we're going to think of heat as a reactant or a product here, and that'll help us to determine which way the reaction is going to shift. And here's a little spoiler here. Remember, liquids and solids in an equation have no effect on equilibrium. They can be ignored. In the equilibrium expression, what's the value of a liquid or solid? What value do we get it? What number value do we give to it? One number. We give it a 1, which we don't show it. Okay, so we don't include that. So that's a trick. Watch out. That's a trick. So your mission, ladies and gentlemen, is to determine which way the reaction is going to shift. Very similar to the K versus Q, which was on the quiz. Which way is it going to shift? Now, because I'm on Zoom, I'm not going to be able to play that video. It's just a little funny little video, and this Frenchman tells you how to pronounce LeChatlier, and he does it several times. Thank you. But if I hit that, it's going to mess up my Zoom because I know from before, so I'm not going to hit it. But you can watch it if you want. It's just for fun. But in other classes, I've usually had someone who speaks French, and so they say it, and it really sounds good the way they say it. But I have no French speakers. Usually I have some French speakers from Africa or from Haiti, but this class, nobody speaks French, so it doesn't sound as good when I say Le Chatelier. When a Frenchman or a French woman says it, it sounds really good. Do you speak French? Zoe, do you speak French? Zoe? Okay, say Le Chatelier, nice and loud. But she doesn't want to do it. Okay, that's all right. No problem. Anyway, you can watch the video. He does it. He's funny, the guy. So, again, when a chemical system at equilibrium is disturbed, it's going to reestablish equilibrium by shifting. In other words, if you stress a system, it's going to act to relieve the stress. If I have a balloon, okay, what happens if I press on this part of the balloon? What happens? The stress, it makes the other part get bigger. So that's the idea. You add a stress, it's going to relieve the stress. And again, you can change, the stress would be changing concentration of reactants or products by removing or adding them, or by adding heat or removing heat. And this is a little trick. We're going to think of heat as a reactant or a product. Okay? So when I say I'm increasing the temperature or decreasing the temperature, What I mean is that I'm adding heat. So if I increase the temperature, I'm adding heat. If I decrease the temperature, I'm reducing heat. I'm removing heat. And keeping that in mind, it makes it much easier to figure out which way the reaction is going to shift. And like everything, this is kind of fun. At least it's fun for me. And again, you can change pressure. And that's the case when you have all gases in the reactant. You can do this by changing the volume. If you decrease the volume, you increase the pressure. If you increase the volume, you decrease the pressure. There's an excellent video. This gentleman, I don't know his name, but he's very good, very enthusiastic on LeChatlier Principle. So I recommend it if you need some more reinforcement. You don't have to watch it, but all right, again, here's the principle. You should know this principle. If you somehow change the system at equilibrium, it will shift left or right to offset the change and reestablish equilibrium, okay? So that is LeChatelier's principle. Keep repeating it. Now, here's a trick to solve the question, which way is it going to shift? You should think replace or replenish or consume. So when you're asked a question about which way a reaction is going to shift after a disturbance, think to yourself, replace or consume, replace or consume, and that'll allow you to figure out which way it's going to shift. Okay, so if you take away products, reactants, products, or heat, the system wants to replace what was taken away. And that'll lead to a shift right or left, forward or reverse reaction. If you add reactants, products, or heat, it's going to consume them. And that will tell you which way it's going to shift. Are you with me? Zoe, you with me? Huh? Yeah. So it's written right there. If you add reactants, products, or heat, the system wants to consume what was added, and that'll allow you to determine which way it's going to shift, forward or reverse, to the right or to the left. Everybody with me? And we're going to get lots of practice. So here's our first. This is kind of fun. So let's start with Zoe here. Well, actually, this isn't a question yet. Yes, it is. First of all, in this equation, what do you notice, Zoe, about ClF3? What phase is it? It's liquid. And all the rest are gases, okay? Gas, gas, gas. So we're going to ignore the liquid, all right? So Zoe, here's the question. What's the effect on the reaction if more oxygen is added? And again, what I want you to do, Zoe, is think, replace or consume. So if I add more oxygen, that's the stress. How will it get rid of it? What will it do? Which way will it shift, would you think? To consume it. Which way would it shift? Right, well, tell me, is it toward the products? Shift right? Yes. Nice. She got it. So we think, replace or consume. We add more oxygen. It wants to consume it now, so it shifts to the right to reestablish equilibrium. Get it? Good. Okay, good. All right, now it's your turn, Gabby. Here's the question. If I remove one of the products, Cl2O, again, you want to think, replace or consume. So if I remove this, how does it replace it? By shifting which way, Gabi? Toward the products or toward the reactants? I'm removing Cl2O. Remember, I say think, replace or consume. So how's it going to replace it? By shifting to the, take a guess. Right, toward the products. You see, because if I take it away, it's going to want to go away. What does that go away? If I take away this, it's missing, so it wants to replace it. There's a gap there, so it shifts to the right to replace it and reestablish equilibrium. Does this sort of make sense? Again, we'll get lots more practice. We got a lot of practice. Okay, Diana, this is a trick question. Adding or removing a solid or a liquid. So notice in the equilibrium expression, in this equilibrium expression, there's no liquid. We don't put liquids there because there's a value of 1. Remember that? We don't put that in there. So what's the effect of removing ClF3 liquid on the equilibrium? Which way will it shift? Trick question. Take a guess. Huh? Neither. You got it. Nice. The trick effect. No effect. If you remove a liquid or a solid, it's going to have no effect because it's not in the equilibrium expression. No effect. Nice. You got that? So watch out for those trick questions. All right. Now, this is not a question, but it's leading to a question. Remember that the coefficients 2, 1, and 3 we can think of as moles. Remember we talked about the mole ratio. The coefficients are the mole ratio. So we can think of this as 2 moles, 1 mole, 3 moles. Ife, how many moles total do we have on the right side? We got 1 plus 3 is 4. You said 4, right? And the left side, how many moles do we have? On the left side, on this side? No. Remember, liquids don't count. Well, that's good. I'm glad you said that because you got to watch out. This guy doesn't count. So only have 2 moles. We don't count this because liquids are 100%. They're not a concentration. Like concentration is moles per liter, but a pure liquid is it's just one liquid. So we just give it a value of 1. Go ahead. Because the 1 only it goes into the equilibrium expression equation, not the KEQ equilibrium expression. So we ignore it in terms of number of moles. So watch out for that. So now, still on you, Ife. So let's say I increase the pressure. Now think about this. The stress is pressure. When there's more pressure, there's going to be more collisions. The molecules are hitting each other more because that's what pressure is. Collisions of molecules on the sides of the container. So if I add pressure, it wants to reduce it. So how would it reduce pressure? It would move which way? So here you have 4 moles. There you have 2 moles. So which way would it shift? Left, toward fewer moles because it's less pressure. Okay, so fewer moles means less pressure. Fewer moles means less collisions. Right. And then it's going to shift to toward fewer moles because there's 4 moles on this side and 2. So it shifts toward the side with fewer moles. So it's less pressure, less collisions. So that's a little rule of thumb. You could write that down. It's always going to, if you add pressure, it's going to shift toward fewer moles. By shifting left to where there's fewer collisions. I love questions, you know that. All right, we have a timeout. We have a commercial message. Zoe, are you with me? Commercial message. This won't be on the exam. I've mentioned this before, but here I have a structure of cholesterol. When it's hit by sunlight in the skin, it gets converted to vitamin D. I told you the famous story in England, probably was like the end of the 1800s. There was tremendous smog in the city. It was the beginning of the Industrial Revolution. It was blocking out the sun, and the children were getting a disease called rickets, where their bones become very brittle. And it turns out because they weren't getting sunlight, they weren't getting enough vitamin D. So how do we solve that? And to this day, how do we solve that? What do we put in milk? Do any of you shop at the grocery store? And if you get a carton of milk, what does it say on there? It'll say vitamin D added, right? And it also says homogenized. or homogeneous. Remember we said that milk is a colloid because the milk fat, by spinning it around, it becomes a colloid and it stays suspended. It's a large particle. Okay? So milk is a homogenized milk is a colloid. It's a solution. Anyway, so and by the way, so that's just for fun, but it's interesting. You see how the structures are similar? Now, let's see if you're awake. What other reaction do you know of that needs sunlight to proceed? Yes, hugely important. Photosynthesis needs light and also needs an enzyme, which is chlorophyll, the green chlorophyll. Good. All right. Back to our regularly scheduled program. And I think it's going to be Akil's turn. But before we get to your turn, I want to emphasize something about changes in temperature. So we're saying that if you increase temperature, you're adding heat. If you're decreasing temperature, you're taking away heat. Now, this particular reaction, you have to be told this because you wouldn't know otherwise. It's endothermic. How do I know it's endothermic? Because what's the sign, Akil, of delta H? Positive. And that means heat is absorbed. So heat is absorbed in this equation. Now, the way we're going to handle this is we're going to write heat as a reactant or product, depending on whether or not it's endothermic or exothermic. For example, here's an exothermic reaction. Where did I write the heat? As a product. You see that? How do I know it's exothermic? Because it says negative. So I put heat as a product. And then we're going to think replace or consume. If it's endothermic, then we're going to put heat as a reactant because it's absorbing heat. So in this particular equation that I have up above, it's positive because it tells us that. And so I'm adding heat as a reactant. That's important to solve this. Add heat as a reactant. Now, Kakil, if I increase the temperature, it says, will the reaction move forward or in reverse when the temperature is increased? So I'm adding heat. I'm adding heat to this equation by increasing the temperature. So you want to think replace or consume. So which way is it going to shift? Yes, yes, you got it. It's going to consume the heat, so it shifts to the right. So increasing temperature of some reactions will favor shifting to the right. Only endothermic, though, only endothermic. Okay. Okay. So if it's endothermic, what does endothermic mean? Say it louder. You're adding, it's absorbing heat. So can you see in this equation that it's absorbing heat as it proceeds to the right? And so if you increase temperature, you're adding heat. And we think of that like a reactant. So it wants to consume or replace. In this case, it wants to consume it, so it goes to the right. We'll get more practice. Now, again, ladies and gentlemen, by the way, Akil, we're outnumbered today, big time. That's okay. I don't mind it. It's nice being around pretty ladies. You know what I'm saying? I gave you all ladies. I just gave you a compliment. Now, um, I forgot what I was going to say. Anyway, let's go next. So it wants to consume the heat shifts to the right toward the products. All right. Um, let's go to Ivana. Here we have calcium carbonate. What phase is that, Ivana? And by the way, calcium carbonate, one of the places it's found is in chalk. That's calcium carbonate. It's also found in antacids, like tum to tum tum. There used to be a commercial, tum to tum tum, about Tums as an antacid. So it has some calcium carbonate in there. So if you look on the bottle of an antacid, a tablet, it'll say calcium carbonate. And then we have, what's the phase of this product here, calcium oxide? Ivana? solid, and then this is a gas. So we're going to ignore, sorry, calcium carbonate and calcium oxide. We're ignoring you. We are ignoring you. All right. So here's the question. What happens to the equilibrium when additional calcium carbonate is added to the system? The equilibrium will shift toward the products, or B, it'll shift toward the reactants, or there'll be no change in equilibrium. For $1 million, what's your answer, Ivana? Nothing happened. You said nothing happened. So I have these earphones on. So yeah, you're right. Outstanding. You just won $1 million. Virtually. Okay. There used to be a program on TV, and the guy who did it, I forget his name now. He passed away, but he was from my university. He graduated from the same university. I graduated from the same university that he graduated from. I can't think of his name, but anyway, then that was a good show. All right. So adding or removing a solid or liquid will not affect the equilibrium, okay? I think you asked a question about that, Zoe, didn't you? It will not affect the equilibrium. All right. Now it's Zoe's turn. We'll get to this delta H later, but Zoe, right now, can you tell me in this particular reaction, is it endothermic or exothermic? And how do you know? Yes, and how do you know that? Because it's positive. It doesn't, I mean, to emphasize it, I would put the plus sign, but if they don't put a plus sign, it's still positive. Now, Zoe, what's the phase of H2O2? Liquid, and then the other two are gas. Now, Zoe, if I add more H2, again, you want to think replace or consume. Replace or consume. Which way is it going to shift if I add more H2? So it's going to shift to the left toward the reactants. Good. Because the stress is, see, right now it's happy. It's at equilibrium. Yeah, it's happy. It's at equilibrium. The concentrations won't change anymore. Even though the forward rate equals to the reverse rate, it's stable. Let's put it that way. I said happy. It's stable. Now I add more H2. Now I knock out the equilibrium. So to reestablish it, the stress is adding H2, so it wants to remove some of the H2, so it shifts left. It consumes the H2. Does that make sense? Doesn't matter yet. It's only going to be affected by temperature. We'll get to that. Good question, though. She said yes. Oh, just a minute. She said, what if its delta H was negative? It's not going to affect adding reactants and products. It will be affected. It will affect the temperature change, though. Okay, go ahead, Ife. Okay, so this is what he discovered, LeChatlier, that the stress, so for those in the viewing audience that I'm recording, the question was, how do you know if you add more H2, it's going to shift to the left, because what he discovered was that the stress is adding more H2. That messes up the equilibrium. So there's too much H2, and so it'll consume it by shifting. Yeah, that's okay. Okay, Gabi, what happens if I remove what happens if I remove O2? Which way will it shift? To the right, because it wants to consume it. Now, Diana, you get the tricky question. If it's endothermic, if temperature increases, we're adding heat. So what we do is we add heat to the equation. Where would I put the heat? As a reactant or as a product if it's endothermic? Reactant. Good. And so now if I add heat by increasing the temperature, which way will it shift? No, it wants to consume the heat. That's the stress. So that's a stress. It wants to consume it, and so it's going to shift to the right. So remember, think replace or consume. Replace or consume. If you add heat, if you add more heat, that's a stress, so it's going to shift right to consume it. This is what LeChatlier discovered. So he could predict ahead of time which way it's going to shift. Think about it. No, you don't have to be sorry. I'm happy. I love questions. Go ahead. No, but in this case, it's being added to the reaction for the reaction to proceed. You got to add heat to it. It's endothermic. Doesn't produce any heat. It absorbs heat. It absorbs heat. So if you add more heat, that's a stress, and it'll try to consume it by shifting right and use up the heat. And then it reestablishes equilibrium. Okay, well, we'll get more practice. But now I remember what I wanted to tell you. You should, at the first chance, review notes from your class, especially this class, but every class. Okay, and if you do that, Aoife, you'll see, you'll start to sink in more. And then if you have further questions, send me an email, or the beginning of the next class, ask me. Write it down and ask me. I used to do that, actually. I would ask the professor of the next class, what about this? I don't quite understand that. And he would explain it to me before class. Okay, yeah, Akil, if the volume is reduced, now, first of all, what happens to the pressure when you reduce volume? Pressure increases. And let me show you a little picture. You see here the same number of gas particles. Which one has more collisions? This one does, right? Because there's a lot less room. So by decreasing the volume, you increase the pressure. That's what I wanted to show you. You should know that. So a way to talk about pressure changes is say volume change. And then you got to figure out what does that do to the pressure. In this case, since the volume is reduced, the pressure goes up. Now, if the pressure goes up, is it your turn, Akil? Which way is it going to shift? Now you got 2 moles here and 0 because this doesn't count. No, see, there's more collisions here because there's more moles. So it wants to shift toward fewer collisions, and there's no moles over there. So it's going to shift to the left toward fewer moles to reduce pressure. So the way to reduce pressure is moved in the direction to fewer moles. In this case, there's 0 because we don't count the liquid. So it's going to shift to the left. Okay? We're going to get plenty more practice as we go. We got plenty more practice. So now we come back to Ivana. You got one of these type of questions again, Ivana. First of all, what phase are all the babies in? The reactants and the products, those are the babies. What phase are they in? Gas. When the following reaction is at equilibrium and the volume of the container is decreased. So first of all, you have to ask yourself, what happens to the pressure when you decrease the volume? It increases the pressure. Anytime you increase the pressure, it's going to go toward fewer moles. Okay? How many moles do you have on the left side of the equation? What's the coefficient here? 1, so just 1. How many moles here? 1 plus 1 is? So you got more moles here, so it's going to shift toward fewer moles. So will the forward reaction rate increase? The reverse reaction rate increase? Reverse increase? Or the okay, which is it, A, B, C, or D? That's the picture again. You got it. So everyone see that? It goes toward fewer moles. Good. Yes, you will. All right, now, it's because there's fewer moles on this side. There's only 1 mole there. There's 2 moles there. So there's more collisions now. When you add pressure to it, it wants to reduce the collision, so it goes toward fewer moles. And so there's less collisions, less pressure. So the stress is more pressure. It wants to relieve the stress by reducing the pressure. Yeah, the liquid you just ignore. Zero. Liquid is zero. Oh, here it's gas, so it's only 1 mole. It's only 1 mole. This is one. 1 plus 1 is what? 2. So it's 2 moles. So it wants to go toward the 1 mole because there's fewer moles. Okay? Well, it just means that it's going to go this way. And so the rate temporarily will increase because it's shifting to the left. So it's the first time we've worded it that way. But basically what it means is shifting to the left. And if it shifts to the left, then that rate increases temporarily, right? The speed increases because it's shifting to the left. Okay, that's a good question though. Think about it. All right, now Zoe, you get the more difficult question, but this is fun. So we have to think this through. You might see this on the exam. A question like this. For a certain reaction at 25 degrees Celsius, the value of K is 1.2 times 10 to the negative 3. And at 50 degrees, an increase in temperature, right, Zoe? The value of K is 3.4 times 10 to the minus 1. So we're increasing the temperature. We're doubling the temperature. Now, which K value is bigger? 1.2 times 10 to the minus 3 or 3.4 times 10 to the minus 1? Which is bigger? Right. So in other words, it's 0.34 and the other one is 0.0012. So the K is going up. If K is going up, if K is going up, what are we increasing in the reaction? Here's the products are C and D. If K gets bigger, we're getting more C and D, right? So if I wanted to add heat, I'm adding heat and the reaction's shifting to the right. So where should the heat go in the reaction? It should go, okay, think about it now. If you add heat, because we increase temperature and it's shifted to the right, how do we know it's shifted to the right? Because they tell us K gets bigger. How do I know K is bigger? Because you're getting more product when you added heat. So it has to be on this side of the equation. And so it has to be endothermic. So you may see this, make a note of this. You might see this type of question on the exam. Heat was added. How do we know that? Because temperature increased. The K got bigger. The K got bigger. How do we know that? They tell us the K got bigger. Well, if the K gets bigger, you're getting more products, right? Here's the K, and you're getting more products, so it gets bigger. So if you get more products and you're adding heat, the heat has to be on that side, so endothermic. Yes. So she said, the question was, if K goes down, would it be exothermic? Yes. Because then the heat would be on the other side, and then it would go this way, and you get more reactants, and that would make K smaller. Good question. So make a note of this question. This is a good one. I like it, and you might, like I say, you might see it again because you have to think it through. A couple things. You got to say, okay, I'm adding heat, and K's getting bigger. So if K's getting bigger, then I got to go. What I would say on the exam, first thing you do on the scrap paper is write this out. Write an equation and write this out to help you. Or even if you come to a question like this on your scrap paper, write this out, and then it'll help you to figure it out. Good. Okay, Diana, I guess Gabi stepped out. Now, the reaction is exothermic. It releases heat, and the temperature of the system is raised. So now what's going to happen? So here, see this equation up here? We're saying that it's exothermic. So the heat's over here. So as heat is added, which way is it going to shift? To the left. So that means it's either going to be A or D. And it shifts to the left, okay? That means we're getting more A and B, and K is getting smaller. You got it. So which is the answer then, A or D? D. Quiet, please. Quiet, please. That's what they do in tennis. When there's a good play in tennis, the fans start clapping and then they go, quiet, please, quiet, please. So you made a good play, Diana. And she understood it. She shifts to the left, and K has to get smaller. Because it shifts to the left, getting a larger denominator. Let me move me. And we're getting a larger denominator and a smaller numerator. So this K is smaller. So D is the answer. You might see this type of question again too. Nice, Diana. Very nice. Quiet, please. Quiet, please. Okay, now you have another turn like you wanted. Well, actually, this one do on your own. It gives you the questions, then it gives you the answers. Here's another one I want you to do on your own. Same thing. It gives you the questions, and it gives you the answers. Of course, solve it without looking at the answers. Another one to do on your own. And now we're going to have some more practice. The final practice for LeChatlier. So here's our equation. Ife. Heat. Why did I put heat there? Because I'm telling you that delta H is positive. It's endothermic. So N2O4 is a gas, and then it forms two moles of NO2. So in the first case, it says addition of N2O4. Which way will it shift? To the right or to the left? Ife. You got it. Once it consumed. Akil. What happens if I add more of NO2? Which way will it shift? If I add more NO2, that's the stress. Go away. Why does that thing go away? So which way will it shift? To the left, because it wants to consume it. Okay. Question, yes. No, no. That's because think replace or consume. If I add more NO2, it wants to consume it, and it goes that way. It wants to use it up and reestablish equilibrium. Hey, think about it some more. Please go over your notes today. Ivana, what if I take away N2O4? Which way will it shift? Right, to the left. Because remember thinking consume or replace. In that case, we want to replace it because we took it away. What if I remove NO2, Zoe? To the right, it wants to replace it. Quiet, please. Quiet, please. Quiet, please. Addition of HE, trick question. Is HE in this equation? No. So will it have any effect? The answer is no. So what's the answer? No effect. Let me ask you another one. If I decrease the volume, which means increase the pressure, and this is where the moles comes into play. There's 2 moles here and there's 1 moles there. If I decrease the volume, what happens to the pressure? Gabi. Increases, so which way will it shift? Left, toward fewer moles. And if I increase the volume, Diana, what happens to the pressure? It goes down. The pressure goes down, so it'll go toward more moles. So which way will it shift? To the right. Good. Now, okay, if I increase temperature, now notice that we're told it's endothermic, Ife. So I'm going to add heat to there, and then which way will it shift if I increase the temperature? To the right. And then Akil, if I take away heat by decreasing temperature, which way will it shift? To the left. So this is a good practice. You cover up the right-hand column. Did you say left? Oh, we didn't. Let's have quiet, please. Let's have everyone clap for Akil. Nice. Okay, so I'm just going to quickly, I'm not going to read all this again. So you can read it again. It's a good review. And there's a very nice video. Good old Professor Dave goes over these concepts again. So if you need more practice, watch Professor Dave. Now, I'm going to give you a handout. Ladies and gentlemen that are watching this, I'm going to give a handout, and I'll give it to you next time if you're not here. These 2 pages. What this does is, Samaya, you know Samaya Gross? So she asked me this question. She said, can you write this up on a review sheet? So yeah, I'll do that. So I did it. So these are all possible. situations that determine ship. Thanks for my approach with this. I made this up. And actually, Mrs. Kelsey typed it up for me. It was nice of her to do that. Does everyone have one? Put your name on it. This is key. Put stars, and these two will go for the people that aren't here today. So this has all the scenarios, and you can look at this in your homework. Okay, so okay, here I am back again. I'll pass this out to you if you weren't here. So again, to close here in the final minute, LeChatlier's principle is reality. This is the way nature behaves, and let me just finish talking about. There's only one more slide after this, but that's okay. We don't need to finish. I want to talk about the Haber process. Okay, so first of all, what Mr. Haber did. See, it turns out in reality, I mean, in practice, when this reaction occurs at room temperature, you get hardly any ammonia. So the first thing he did was increase the temperature to a very high temperature. And so can you see that it would produce more ammonia that way, Gabi? The second thing he did, which was brilliant, and it's using LeChatlier's principle, what he did was every time ammonia was formed, he took it away. How did he do that? He had this tube that cooled the gas, and it would liquefy and go away. And therefore, which way would it, if I take away ammonia, which way does it shift? To the right. No, to the right. If I take away ammonia, it shifts to the product, right? So that solved the problem. Every time ammonia gets formed, he'd take it away, and it would keep the reaction producing ammonia. How did he take it away? He condensed it. So he had the gas go through a cold tube, and it would become a liquid and go away. And then it would keep going forward, and by adding the heat. And that's how he solved the problem. And so now we make tons and tons of ammonia, which is used in fertilizers, which is very important for growing food. Ladies and gentlemen, I have good news. Class is over. So have a very, very restful Sabbath and get recharged. And let's do this again on Monday. Okay, bye-bye, everyone. Now I'm going to turn this off. How do I turn this off again? Oh, stop the share. Bye, Zoe.